Let's pick up where we left off. I personally do not like spiders, and this one actually kind of creeps me out because it says, what if you had 26 spiders on you and they each have 8 legs, and you're like, how many spider legs do you have, like, running over you? So it's 8 times 26, right? Okay, so we're going to kind of change that from spider into a molecule. Instead of legs, we're going to change it into atoms or molecules of atoms. But we could do this factor label, and it looks like this. So first off, we buy the fact that, do you see we have a little ratio up there? There are 8 legs per 1 spider, right? Okay. So the way this problem would work is the first term would be the 26 spiders, which really creeps me out, 26 spiders over 1. And then do you see if we just take this ratio and bring it down, our spiders will cancel, we'll be left with units of legs. So if we take 26 spiders over 1 times 8 legs over 1 spider, units of spiders cancel, and we're left with legs, which was what we were after. How many spider legs are there crawling on you? Okay, so this is kind of a weird one. We've talked about rounding, and these are exact. I guess it's not so weird. Every spider has exactly 8 legs, and we have exactly 26 spiders. We don't have half a spiders or anything like that. So we actually we round according to, well, there's no uncertainty brought. So our decimal displays 208, and we keep all of the significant figures. So, all right. So let's take this up to compounds. So we have this carbon tetrabromide. Remember, you guys aren't using the prefix tetra in any of your stuff that you're going to make, no tetras. But the reason we use tetra here is because this is not an ionic compound. This actually is a molecular compound. I know that because there's no metal, and I can use tetra there. Anyway, so let's just say we have a certain mass of the compound, and we have gone from mass of the compound to moles of the compound. That's what you guys did for your homework, okay? But now we don't want moles of the molecule. We want moles of just the bromine atoms. So it's kind of like spider legs, okay? So we just want, bless you. You would tell me that we have, what, 4 bromine atoms for every CBr4 molecule, would you? Kind of like 8 legs for every 1 spider. And we're going to use that to our benefit. Okay? So again, we get this whole, since we're after bromine atoms or moles of bromine atoms, we have to kind of dissect it to know that in 1 repeating unit of the molecule, since the formula CBr4, we have 4 moles of bromine in 1 mole of the compound. So again, you can kind of see we've got the whole like little ratio going, and we can use it to work this problem. So to work this, it's going to start out kind of like our other problems. We're going to have to go from the mass that was given to the mass of the compound to the moles of the compound. So you guys did some homework with that. We're going to use the molar mass. We're going to use the periodic table. And here in my solution, I'm going to show how we're going to take 1 carbon plus 4 bromine, add them together, get the molar mass, and use that as a conversion factor. But now once we have moles of CBr4, to get to moles of Br, we're going to use that ratio, 4 moles of Br for 1 mole of CBr4. So it's missing my thing there. I'll write it in there. This one is 4 mole Br for 1 mole CBr4. And we're done. So you can see the top there is the molar mass of CBr4. Now on your test on Thursday, you're going to have to show me your molar mass calculations. Okay, when in doubt, write it down. So from the periodic table, I would take 1 times 12.01 for carbon, plus 4 times 79.90 for bromine, round to 2 decimals, and I get a whopping 331.61 is the molar mass. So 331.61 grams per mole for that compound. So let's go ahead and string them up. Okay, so the first term is going to be that 1.92 grams of CBr4. Now, in this case, I do think that you have to be explicit. You have to say CBr4, grams CBr4. I put it over 1, and then what does the next term look like? I think. Yep, over that 331.61 grams. I'm liking it. 1 mole of CBr4 over 331.61 grams of CBr4. Perfect. So if you kind of keep up with units that cancel as you go, which I do sometimes, my grams of CBr4 have canceled. I'm left with moles of CBr4. Now what do I need to do? What did it, yeah, perfect. 4 moles of Br over 1 mole of CBr4. Perfect. And then our moles of CBr4 cancel. We're left with moles of Br, which is, we're done. I haven't done it recently, but one of the times, I've taught this before, and I like pass around the tablet, and everybody has to fill it in as it goes around. We might try that someday. The other thing I need to mention is, remember I said that Wednesday we are going to go ahead and have a review. I'm not even going to play games with you. We're going to do a review. But I said attendance needs to be good because that will dictate whether or not we have a review for Unit 4. So if nobody comes, then I'm not doing it again. Okay, so we'll just see. But we're going to do that. All right. So round to, looks like 3 significant figures because of the 1.92. So rounded to 3 significant figures, I got 0.0232 units or moles of bromine. That's it. That's like spider legs. I think I'd rather bromine than spider legs. Okay. So this slide just kind of warns you that when we have moles of different things, like for instance, we had moles of CBr4 first, and then we had moles of Br, you have to be explicit and like hit you over the head with what it is. So, all right. Looks like I have one more problem. And in this case, we're given a compound. Sometimes, if read it a few times and see we're given a compound of a mass of a compound. The compound has 4 carbons and 10 hydrogens in it, and we want the grams of carbon. So actually, we don't want, for instance, the number of spider legs, but we want the mass of the spider legs. Okay? So to work this one, can you see where we're going to start with that mass of butane, and we're going to go to moles of butane using the molar mass, and then we're going to go from moles of the compound to moles of carbon, because we're after mass of carbon, but we're going to go to moles of carbon next. So to get from moles of compound to moles of carbon, it's going to be what? That 4 moles of carbon per 1 mole of C4H10. And then we can't stop with moles of spider legs or moles of carbon, but we need mass. So how can we go for, yep, to go to grams, we're going to use the grams, the molar mass of just carbon off the periodic table. Exactly. Oops. And I'll tell you, if you look at the periodic table, the decimal number for carbon is 12.01 grams. So 12.01 grams of carbon per 1 mole of carbon. And actually, that's going to be our last term. So when you work these in your homework and on a test, I'm going to have to see this first step. So the molar mass of the compound. We take 4 times 12.01 plus 10 times 1.008, rounded to 2 decimals. It's 58.12 grams per mole. I must already have that one. So here we go. The first term is going to be the mass of the compound, 1.92 grams of C4H10 over 1. And then what does the next term look like? Anybody?
The 58.12 grams on bottom.
Yep, I'm liking it. He's going to put 58.12 grams on the bottom. 1 mole of C4H10 over 58.12 grams of C4H10. Perfect. And then what about the next one? What do you think?
4 moles of carbon over 1 mole.
Perfect. 4 moles of carbon over 1 mole of that other thing. 4 moles of carbon over 1 mole of C4H10. Perfect. And then last but not least, what's the last term?
12.01 grams of carbon over 1 mole.
I'm liking it. 12.01 grams of carbon over 1 mole of carbon. Perfect. How many sig figs do we need to round this to?
Maybe 2.
2, 3. Why 3?
190.
Yep, 192. Round to 3 significant figures. And I get 1.59 grams of carbon. Let's see if Tyler gets the same thing. See? Massive spider legs. All right. Guess that brings us to an assignment slide. Dun, dun, dun. Okay. So these will be due on Wednesday.
On what day?
Wednesday.
What?
Wednesday. It is Wednesday. And here's what they look like. So let's not make this harder than it needs to be. This actually is a baby problem of what we did, because now look, they give us the moles of the compound and they want moles of carbon. So it's just a quick shot. In fact, for A, I went ahead and said, if you're going to go from 2.5 moles of CH4, the fact that the subscript is 1 here means that you have 1 mole of carbon for every, I mean, that's it. You're done. So those shouldn't be too bad. Oops. The next one looks like this. And the next one is a full-fledged, more of a full-fledged problem. Da, da, da. Come back here. Here it goes. Okay. I went ahead and showed you what it looks like. Yeah. Okay. I think you're good with that. Okay. So now in this one, it's a little different. We're kind of going for the mass of the spider legs, okay? They give us the mass of the compound, and if you want to, oh, we had some problems for extra credit, didn't we, that you're handing in today? I need to make a mental note. If I hand back something that I said I would give extra credit for and I don't, say, hey, Snipes, this is extra credit. because I just forgot, okay? Because I want to go ahead and do that again. I want to go ahead and, since these are so similar, if you want to do these extra ones, you can do them for 10 extra credit points. I know, because I'm just like, A, B is so similar to C and D. So go ahead and A and B for full credit, C and D for 10 extra credit points. But like I said, remind me if I forget. So in each of these, you're going to start out with 38.0 grams of compound. And you're after grams of chlorine in that mass of compound. So you're going to go from grams of compound to moles of compound. Show me calculating the molar mass, okay? And then you're going to use that little, from the formula, you know, X moles of chlorine for every 1 mole of compound to get to moles of chlorine. And then how are you going to go from moles of chlorine to grams of chlorine? Molar mass from the periodic table. And I even looked it up for you. The decimal number for chlorine is, I think it is it 35.45? Yep. So that is the molar mass that you'll use at the tail end. Okay? So that's it. Any questions? Massive spider legs. I've been thinking about like frog legs, so you get like a couple pounds of frog legs, a couple pounds of spider legs. Okay, so those 2 are due Wednesday for extra credit. Wait, for normal credit and 2 for extra credit. All right, so on to finish up with this last part. And it looks like this. And these are kind of fun problems. They're kind of, well, you'll see. It's kind of a classic chemistry. It's a classic concept in chemistry. So we've been talking about chemical formulas. You guys would tell me the chemical formula for water is H2O, okay? And so we actually then can dissect water to see what, in a water molecule, what mass is brought by hydrogen and what mass is brought by oxygen. Now, hydrogen are pretty light, so that weight percent would be pretty light. Oxygen, a little bit heavier, even though there's only just one of it, okay? So there's this problem where we basically dissect compounds and say how much by weight each element brings to the table. So I'm just going to jump in and show you an example. We could be dealing with acetone, and the formula for acetone is C3H6O. And we need to know the weight percent of carbon, the weight percent of hydrogen, and the weight percent of oxygen in that compound. So there's a couple of different ways to do this, but what I'm going to advise to you is this way. Think of 1 mole of the compound. Think of 1 mole of the compound. Now, what is the mass of 1 mole of the compound? The molar mass of the compound we can get off the periodic table. We take 3 times the decimal number for carbon plus 6 times decimal number for hydrogen plus 1 times decimal number for oxygen, okay? So that's the total molar mass. Are we all okay with this? Okay. What's that?
Yes.
Okay. Then if you take as your basis, in that 1 mole of compound, you buy this, that the mass brought by carbon is 3 times the decimal number for carbon. The mass brought by hydrogen is 6 times the decimal number for hydrogen. And the mass brought by oxygen is 1 times the decimal number for oxygen. So those are the relative masses in 1 mole of compound. And do you guys remember, like, way back when we did your measurements lab, and you guys took your eggs, some of you guys are better than others, like taking your egg apart into the whole shell, white and yolk, okay? But at the end, what you guys did was to get a weight percent of each of those components, you took the mass of the component and you divided by the whole egg. And that's exactly what we're going to do. We're going to take those 3 individually and divide them by the total mass, okay, to come up with the weight percents. And it looks like this. So for carbon, if we take 3 times 12.01 divided by your total mass, divided by 58.08 grams of compound, 3 times 12.01 grams of carbon divided by 58.08 grams of C3H6O. That's a weight percent. Well, that's actually a mass fraction, or weight fraction. Take it times 100, and then you're getting to percents. And I don't know if you guys remember, but with your egg, I said you still follow the rules of rounding. The 3 is exact, but there's uncertainty in the 12.01 and the 58.08, so 4 sig figs. So you should get a weight percent of carbon is 62.04%. And that same pattern then is we use to get the weight percent of hydrogen and then the weight percent of oxygen. And they should add up to be equal to how much percent? 100%. So here we go for hydrogen. We take 6 times 1.008 grams of hydrogen divided by the total mass of the compound, 58.08 grams of C3H6O, times 100, round to 4 significant figures, and I get 10.41% hydrogen. Now, some students would say, well, Mrs. Snipes, can't I just get the oxygen by difference? And yes, you can. But let's do it this way. If we take 1 times 16.00 grams of oxygen divided by 58.08 grams of compound, C3H6O, times 100, and round to 4 significant figures, dun, 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 we get 27.55%. So if you want to put exam on this, you can, because there will be one of these on your test, which actually, that's one of the things we'll do right off the bat on Wednesday. We'll take a look at that review, that sheet I gave you. And I brought you a copy, JC. Yeah, it's number 11 on the sheet I gave you. Remember on Friday I gave you one of this, kind of outlined for the test? That's what this is. You want to put number 11 on there. So you're welcome. They're kind of fun. You have to show all of your work though, okay? Because you want the full 5 points or whatever it is. All right. So yes, a quick check. If you add them all together, you do get 100%, 100.00%. Now, if it's off by 0.05 or something like that, don't worry, it's probably just rounding. But if it's off by like 10%, then something's wrong with your weight percent calculations. All right. So this one will be due also on Wednesday. Let's take a look at that. It looks like this. And this is going to get confusing. I hope I don't lose track of all the extra credit, but this is this sort of week. So since these are so similar, I'm going to make them worth extra credit points so you don't totally get sick of these problems. So you can do the first 2 for regular credit and the last 2 for extra credit. Any questions? Okay. And so I actually just kind of have a little hint of how that goes. Just to remind you what we just did, you calculate the total mass of the compound, and then you divide the mass of the element by the total mass of the compound. So here I have element moles, you get that from the formula, and element molar mass, you get that from the periodic table. So you should do fine. Okay. Skip the next problem. Dun, dun, dun. This is actually from last semester. There's no need to confuse you because I do want to look at one more concept that is important when we talk about compounds. So when we talk about compounds, we're used to just saying the way it is, the molecular formula, the real deal. But there's something called, for a compound, its empirical formula that is sometimes a reduced form of the molecular formula. So chemical formula just tells you what the compound is. Okay? If you can divide the number of atoms of each type of element by a whole number and get a new set of whole numbers, okay, that reduced form is what we call the empirical formula. It's easier just to kind of show you. So it looks like this. Okay, if we pick on butane, notice that notice that the numbers 4 and 10, the subscripts of carbon and hydrogen, I can divide by 2 and get another set of whole numbers. So if I divide 4 by 2, I get 2. If I divide 10 by 2, I get 5. Yep. So these are just divided by 2. Okay, and so that means that this reduced form over here is the empirical formula of butane. So empirical formulas are awesome. They tell you what elements are involved, and they tell you what relative numbers of atoms of each type of element, but they don't give you the exact picture. Now, not all things can be reduced. Like water, you got the whole 2 and the 1 going on. No, you can't divide by a whole number and get another set of whole numbers. So in that case, the molecular formula and the empirical formula are the same. Let's see. Hydrogen peroxide, H2O2. This is my favorite Christmas molecule. Okay. Ho. So you can divide the 2's by 2 and get 1. So the reduced empirical formula is HO. Hydrazine, N2H4, of course you can divide both by 2 and you get NH2. It's the empirical formula. These last two are among my favorite too. So acetylene is C2H2. Of course it can be reduced to C1H1. And benzene is C6H6, which can also be reduced to the empirical formula CH. So I think this is cool that they have the same empirical formula. Okay, but these are totally different compounds. Cool. So actually, when we did the weight percent problems, okay, the weight percent gave relative amounts of each element by weight, and the empirical formula gives relative amounts of each compound by relative moles. So the percent elemental composition gives it a mass. The empirical formula gives it on a relative mole basis. So remember the one I liked the acetylene and the benzene a minute ago, the C2H2 and the C6H6? If you were to go to see what the weight percent of carbon and hydrogen is in both of those, acetylene and benzene, they would have the same weight percents of carbon and hydrogen in both compounds. Kind of makes sense, I think. Everybody's sleepy today. Now this, I almost didn't show you this semester because I never really want to confuse you. But there are a few things that you don't reduce. One of them is that annoying mercury 1 polyatomic ion. Mercury 1 is this, mercury 1 is Hg2, 2+. That is mercury 1, and you don't reduce it. And another thing that you don't reduce, a polyatomic ion, is NH4+. The name of that, of course, is ammonium. And you wouldn't reduce it either. So if given a chance, for instance, I'll change my color to blue here. If given a chance, if you were dealing with mercury 1 chloride, it kind of looks like you can divide these both by 2 and get 1, but don't do it because then you're breaking up that mercury 1 polyatomic cation. Similarly, if you get this one took me a minute to look at. If you get this down here, ammonium nitrite, it looks like you can join those two nitrogens together, and what you really have is N2H4O2, okay? And then what you might want to do is reduce it into NH2O, okay? but don't do it. You're breaking up an NH4 plus group that was never meant to be broken up. You won't run into that in my test, but I just kind of point that out. All right, so now these aren't worth extra credit, because let me show you what these are. These will be due also, okay? This is the third part that's going to be due. This is what they look like. These should take you like no time at all. Okay. So your instructions on the slide say to look at 81 again and to look at now 80, and in both cases write the empirical formula.
Oh,
Yeah. So, for instance, you know, I'll put a check mark next to those ones that can be reduced. I bet you buy this: reduced, 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 not reduced. You know. So my checks, just kind of looking at it quickly. Now, sometimes I'll look too quickly and I'll be like, wait, you can't reduce that. But like, for instance, D, if you have 2, 6, and 1, you can't divide by a whole number and get another set of whole numbers. But if you have 2 and 6, you can divide by 2 and you get 1 and 3. I'm glad I'm not a math teacher. Okay, so your instructions were to go ahead and write the empirical formulas for all of these compounds. Remember, if no reduction occurs, then the molecular formula is the empirical formula. Okay? We're getting out early. Woohoo!
I'm gonna stay here.